All right, let's dive into one of the most powerful and, let's be honest, one of the most profoundly weird theories in all of science, quantum mechanics. But here's the twist. Our story doesn't start with the atom. Nope, it begins with a clue, one that was left almost 100 years before anyone even dreamed of quantum physics. And that's the big mystery we're going to unravel today. How on earth did a mathematical idea from way back in the 1830s end up predicting the secrets of the subatomic world, a full century down the road? You should really think of this as a detective story, where the clues are buried deep inside the laws of physics themselves. Okay, so first things first, let's meet the man who, completely by accident, left us this first clue. His name was William Rowan Hamilton, a truly brilliant Irish physicist. I mean, just look at this timeline. It's kind of wild. In the 1830s, Hamilton comes up with this new way of looking at how things move. But his insight was so far ahead of its time that it took physics almost 100 years of crises and massive breakthroughs just to catch up and figure out what he had stumbled upon. So here it is, the heart of Hamilton's clue. On one hand, you've got the motion of a particle, like a ball flying through the air, which is all about mechanics. On the other hand, you've got the path of a ray of light, which is governed by the laws of optics. Now, these two things should have absolutely nothing to do with each other. But Hamilton found that the deep underlying math describing both was, well, it was almost identical. It was the strange, spooky connection that nobody at the time could explain. It just made no sense. For decades, Hamilton's idea was just this neat little mathematical quirk, a curiosity. But as the 19th century rolled into the 20th, the whole world of classical physics, which seemed so perfect, was about to hit a brick wall. And all of a sudden, Hamilton's forgotten clue was about to become the most important idea in town. You know, back then, physicists were feeling pretty good about themselves. The laws set down by giants like Isaac Newton, they worked perfectly. I mean, for everything from planets orbiting the sun to just, everyday objects. It really seemed like the universe was this beautiful, predictable clockwork machine. And then this one simple experiment came along and basically broke physics. It's called the photoelectric effect. All scientists were doing was shining light on a piece of metal to see if it would knock any electrons loose. It sounds simple, right? But the results? They were completely impossible to explain with the rules they had. So here's what everybody thought would happen. The old theory said that light is a wave. So a brighter light is just a more powerful, more energetic wave. It's only logical that if you crank up the brightness, you should smack those electrons harder, making them fly off the metal with a lot more speed. It makes perfect sense. Except that's not what they saw, not at all. In the real world, making the light brighter didn't change the speed of the electrons one bit. It just knocked more of them off the metal. Imagine turning up a fire hose expecting a more powerful jet, but instead you just get a wider one. This result was a genuine crisis. Reality was just not playing by the rules. The solution, which came from Max Planck and Albert Einstein, was just radical. They said, what if light energy isn't some continuous wave? What if it arrives in tiny, discrete packets called quanta? Each little packet, or photon, carries a fixed punch of energy. So a brighter light isn't a stronger wave, it's just more packets being fired. And just like that, the experiment made sense. More packets means more electrons get knocked off, but since each electron only gets hit by one packet, their speed stays the same. This idea of quanta wasn't just some little fix, it was a full-blown revolution. It meant the old rules were fundamentally wrong, at least for the tiny stuff. It was time to write a completely new rulebook for reality, and it turns out the universe is way, way stranger than anyone could have imagined. And this led to one of the wildest ideas ever, wave-particle duality. Okay, so if light waves can act like particles, what about the other way around? Could particles, like electrons, act like waves? And the answer, incredibly, was yes. Experiments actually showed electrons creating interference patterns, just like ripples in a pond. And boom, suddenly Hamilton's 100-year-old clue that the math for particles and light was the same, it all just snapped into place. It wasn't a coincidence. It was practically a prophecy. The fallout from this was just mind-bending. Take superposition. This says that before you actually measure a quantum particle, it doesn't really have a definite state. It's not in one place, it's more like a cloud of all possible places at once. It's only when you look at it that you force it to pick one single reality. And that flows right into Heisenberg's famous uncertainty principle. Now, this isn't about having clumsy measuring tools. It's a fundamental law of the universe. The very act of nailing down a particle's exact position will, by definition, mess up its momentum, and vice versa. It's like a cosmic trade-off. There's a hard limit on what we are allowed to know about the universe. These ideas were so out there, so against every piece of human intuition, that even the scientists who discovered them were completely floored. As one of the pioneers, Niels Bohr, famously said, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. It forces you to just throw out your common sense picture of the world." So this all brings up a really deep question. If the quantum world is this fuzzy, blurry cloud of possibilities, why does our world, the world we see, seem so solid and definite? This is called the measurement problem, and it's one of the biggest mysteries in all of physics. You see, this cloud of possibilities is described by something called the wave function, but the second we observe it, that whole wave of possibilities seems to instantly collapse into one single real outcome. But what causes that collapse? What's the trigger? Is it the machine doing the measuring? Is it human consciousness? We still don't have the answer. And this has led to a huge debate that's still going on. The classic view, the Copenhagen interpretation, basically says, don't ask why. The wave function is just a tool to predict things, and the active measurement forces an outcome. End of story. But other ideas, like objective collapse theories, say no, the collapse is a real physical thing that just happens on its own. It's super rare for a tiny particle, but it happens all the time for big objects like us, which is why our world seems so solid. The legendary physicist Richard Feynman really said it best. He basically said quantum mechanics describes nature as she is. Absurd. We don't have to like it, it doesn't have to make any common sense, but it just works. Its predictions are the most accurate and well-tested in the history of science. Now, I know what you might be thinking. This is all pretty abstract, kind of weird, and doesn't really have anything to do with your life. But you couldn't be more wrong. That 100-year-old clue left by Hamilton, it's the reason our entire modern world of technology even exists. Here's the big takeaway. Every single piece of tech you see here works because we figured out how to use and control the bizarre rules of quantum mechanics. The tiny transistors in your phone, the lasers carrying data across the ocean, the atomic clocks that make GPS possible. It's all powered by this absurd science. So, there you have it. We've drawn a straight line from a strange mathematical pattern that William Rowan Hamilton noticed in the 1830s through a crisis that literally broke physics to a whole new set of rules for reality, and all the way to the very device you're using to watch this right now. That century-old clue wasn't just some footnote in a textbook. It was a map to a whole new universe. And that leaves us with one final thought. The story of quantum mechanics is this incredible reminder that the deepest secrets of the universe can be hiding in plain sight, sometimes for 100 years, just waiting for us to ask the right questions. It really makes you wonder, what other strange clues, what other weird analogies are we staring at right now without even realizing it? What's the next great revolution going to be?